I'm so used to 2 hours. Bro, I snuck out of the door.
I don't like that this is like pretty much like every other day either. I'm used to like
It is. I hope so. There should be like minutes to when it starts. I want all his videos to start when it starts. Oh yeah, if he comes, he's late. There's no
rejection this week.
Dude, he's gonna watch this.
I know. He's gonna be like,
Josh, did you sign up for any clubs?
Huh?
Did you sign up for any
bro,
clubs?
this man invented it. What are you talking
So
about?
he was out there with that club soccer.
Huh?
Club soccer.
Okay, guys. Good morning. How we doing?
All right.
Okay, sounds great. These 2 compounds here. 3 compounds, or is it? Are these the same, or are these different? That's a question. We'll have to reboot this thing because it won't. I don't know how to make it work when it wants to act like this. If you leave it on, it'll go off, and I don't know how to get it back on. If anybody knows how, let me know. 2 alkenes here, hybridization. Both of these carbons sp2 right. Each of them has a p orbital overlapping to make pi bond. Need to know structure, architecture of organic compounds. Compounds here, each carbon is sp3. Of course, these H's, this is sort of shown condensed. The bonds are not fully shown out. This carbon has 2 H's, 4 electron regions, 4 bonds around it. Each carbon is tetrahedral. Geometry, tetrahedral, 109.5, typical bond angles, etc. Here we go right here. Although the H's are black, bromine blue, chlorine green, yeah. Sigma bond between carbons, important about that. There's no pi bond. Because there's no pi bond, sigma bond can rotate, right? Head-to-head overlap. This is a head-to-head overlap of 2 orbitals making this bond. Rotate. You can rotate it like that, or you can just rotate it like this. But the bonds over there, if the chlorine is green, it can rotate compared to the bromine. Okay? And it's 1 compound. It can exist like this. These are all conformers, just like I can exist like this. I'm 1 person. Okay? Because I have some flexibility in my rotation. 1 compound. This here is not 1 compound. This is 2 different compounds. Bromine and chlorine both up compared to the plane of the pi bond. Not necessarily the plane, but it's the same side of the pi bond. Or they could be opposite, yeah? Something like this. I wish these were larger. But these are 2 different compounds because this guy, because of the presence of the double bond, which is a sigma and a pi, the pi you cannot rotate. If you rotate, you break the bond. It's not going to want to do that. So I cannot rotate this around. Okay? Remember, there's a pi bond here. It's not really shown in this model. Okay? Try to rotate this around, you're going to be breaking the pi bond. And so it will not do that under most common circumstances. You can get it to rotate, put in some energy like light. That's common. And sort of promote electrons. We'll talk a little bit about that. So this is 2 different compounds. One where the 2 halogens are opposite, we'll call that trans. And one where they're the same side, we'll call that cis. They cannot rotate. 2 different compounds. They have the same connectivity though. Chlorine connected to this carbon, chlorine connected to that carbon, bromine connected to that one, bromine connected to that one. Connectivity doesn't deal with projection, just where they're connected. Same connectivity. We'll see if this will fire back up. Guys, I sent you an essay from the speaker that's coming in November. He took a lot of time in writing an essay meant for you guys. I know some of you have read it. I hope all of you will read it. I hope it's useful. Okay, it's a wee bit long, but I think it's worth it. As I mentioned in my email, a number of you are, well, most all of you probably are thinking about your future careers. Okay, learning from other folks who have developed and built a successful career. I hope it will be useful for you, particularly with regard to someone who's talking about some chemistry. Now they're in a chemistry field. So Dr. Sabatini is coming in November to give a seminar. Again, he works for the U.S. Army doing work on explosives. Good. I've also sent you other handouts. We'll get to physical properties today. We'll be getting to acid base fairly soon, and then we'll be moving on to the alkanes handout. The alkanes handout contains your nomenclature, which is to be covered by video only. Good, we got this fired back up. Okay, any questions before we get going with where we've left off at? Yes?
Are those constitutional isomers?
No, what's the definition of constitutional isomer? Good question. Different what?
Structures?
No, different what? Different connectivity. Do these have different connectivity? I went through that. No, we have chlorine connected to that carbon or bromine connected to that carbon.
Are they resonant?
Resonance? No, not resonance. Resonance, you only move pi electrons. What pi electrons have been moved? Not resonance structures, yes.
So are they just two completely different?
Well, they are isomers. They have the same formula. If you write the formula out. They're not constitutional isomers. They're stereoisomers. Different projection of the groups.
So that would that be an L and a D? Or is that something?
No, no, these are not enantiomers. There's different types of stereoisomers.
Okay.
Enantiomers and diastereomers. Enantiomers are mirror images. These are not mirror images. The mirror image of this would be,
This.
if you look in the mirror, you would see that, which is also the same size. Yeah. They're stereoisomers that are not mirror images, they're diastereomers. Okay, I think we can look at here since I see this. Okay, any questions about that? How do we do down here? Longest bond, A to C. Which one's longer? A, then next.
C.
B would be next, and then C, yes, A, B, C. A longest, C shortest, right? How'd we do? Any questions about those? Any questions about those? There's warm-up questions to be working. There's questions in workbook, your textbook, etc. Any questions about that handout? They're not in color, but we do have black and white. You can see perhaps a little bit more three-dimension, especially the two sp carbons. You got the sigma bond here, head-to-head overlap. Each carbon has two p orbitals. The two p orbitals are orthogonal to each other, 90-degree angles to each other. One straight up and one straight up over there interacting. And then you got two like this, and they're interacting side to side that way to make a triple bond between the carbons. The other sigma orbital is interacting with the H1s. To have a CH bond on each outside there. Acetylene. So you do have some pictures there. Any questions about hybridization in general? Okay, next handout will be the physical properties. But actually, no. We need to do a couple more examples and get into heteroatoms. Let's get our outline. See where we're at. Other hybridization examples. Carbocations. Let's see. Let's put up something like this. Methane would be CH4. What about just CH3? It's not typical bonding. Carbon doesn't have an octet. It's only got 6 electrons around it. If this is all it is, how about a charge? Does this carbon have a charge? Positive charge, right? Got to be able to do charges. Okay. Well, this is going to be a common type of compound we'll see. It's a carbon cation. Positive cation, right? Okay, that's shortened to carbocation. All right. Carbocations are very common in organic chemistry. What's the hybridization of this carbon? How many electron regions around it? 3. There's 3 bonding regions. Where is the 4th? Out of 4. 3 bonding regions. So what hybridization do you expect? sp2. sp2 means what geometry? Trigonal planar. Okay. So are the bonds drawn appropriately as I drew them? No, that's right. Trigonal planar, correct? So what is trigonal planar? More like this. Trigonal with bond angles of what? Not 90. I drew it as 90, right? Not 120. That's what all this means, right? Bond angles of things, bonds there distributed in trigonal planar. Okay, which ones are coming forward, which ones are going back? Because, by the way, the tetrahedral, we just keep a single 1-carbon tetrahedral with maybe a couple of different things on it. If we draw the tetrahedral, if the black is in the plane of the board, pretend the board's here and that's drawn on the board, one will be coming forward and one will be going back. That's your standard tetrahedral, 109.5. Okay, we'll draw plenty of those. Going forward or back here? No, it's trigonal planar. Solid plane of the board. Okay? As if I had it, it would be just all flat. H is in the plane. 120. That's what we expect. Okay. Now I will ask you to graph this hybridization, sort of like what we did last time. I don't quite get textbooks. They will do a little graphing when they introduce hybridization, and then they will never do it again. I don't understand why. None of them will. I think it's very useful. Incredibly useful. That's why I try to talk about it. I try not to talk about things that aren't going to be useful for you and to help you. Graph the hybridization. Well, we already said it's sp2, so let's start with sp2. How many hybrids is it? 3. What's left over? 1 p orbital. It's always like that, right? Okay. What type of bonds do you see? Here's the process. What type of bonds do you see? I see 3 sigma bonds to hydrogen. What type of orbitals do you use to make sigma bonds? Hybrids. Sigma bond to hydrogen. Sigma bond to hydrogen. Sigma bond to hydrogen. Okay. What's the p orbital being used for? Anything in the p orbital? Is it being used? Oh, it's empty. Empty p orbital. Okay. How many electrons are around their carbon in terms of an octet count?
6.
6. There they are. 2, 4, 6. Not 8. It's 2 missing from an octet. Okay? Why is it a positive charge? Because how many does the carbon own in this bonding? How many did it bring to the dance? How did you determine the charge? It only owns 3 in this, what we drew on the board. It's supposed to own 4. It only owns how many? 3. There are the arrows. 1, 2, 3. There are your 3 that it owns. That's why it's a positive charge. There you go. That's a simple graphing. This is a p orbital, right? That is, in addition to these 3 hybrids interacting with each with an H, what else is there? There's a p orbital. And if I drew it, half of it would be coming out this way and half would be going back. Okay? Or I could do it like this. Okay? There it is. It's like that. Or I can turn this way, and now it's coming straight up. Of course, it's a p orbital. It's half up and half down. Okay? It's perpendicular to that trigonal planar. Or you can draw it like this. Then it would be coming now at you and going back. That's empty p orbital. That's a carbocation. Okay, let's start again. What if we had such a, this? I'm not going to worry about bond angles. We'll address that. But what if we had a lone pair there?
Negative charge.
What's the charge of this?
Negative.
Yes, that would be negative. That's an anion. What do you want to call a carbon that's an anion? Carbanion. Not a carboanion. Carbanion. Here we go. This is a simple carbanion. What's the hybridization do you expect?
sp3.
And geometries and bond angles. It's all the same question. How many electron regions? 4. 3 bonding regions and a lone pair region. 4 electron regions, we would expect sp3. Okay, what's sp3 going to look like? If we graph it, 1, 2, 3, 4, right? It's 4 hybrids. Anything else there? Nothing else there. 4 hybrids. Okay, what type of bonds do you see? 3 single bonds, to H to H. Okay, here's a very hard question for you. Where's the lone pair? What type of orbital is the lone pair in? In the p orbital? Oh, no. We don't have a p orbital. This is all we have. It's sp3. sp3 carbon doesn't have a p orbital. Right? Because all the p orbitals went into the blender and they shot these out. LP and sp3. If it's not there, where is it? It has to be there. Okay? So we got a carbon that's sp3. That means that we got what? We got 2 in the plane, right? 1 forward, 1 back. And what is this ruling? These are ruling orbitals, right? Those are your 4 hybrids. Okay? And then, same old thing, right? H, I'm not going to complete it out here. 2 electrons, right? H, 2 electrons, 1 from H, 1 from carbon. Okay, here. What's in this? Yeah, it's just a lone pair with its own region that contributes and why it's in a tetrahedral. Okay? It's a lone pair. So that's a region. And it's in this orbital, but it's not interacting with any other nucleus to make a bond. These 4 are all spread out here. Bond to H, bond to H, bond to H, and then lone pair. You need to always know what type of orbitals your lone pairs are in, because lone pairs are primary source of reactivity, and depending on what type of orbital they're in, that affects the reactivity. So this was some other carbon ions, carbocations, carbanions. Carbanions are less common than carbocations. We'll see lots of carbocations, but we may occasionally also see carbanions. Atoms other than carbon. Syllabus handout. Okay, let's do one that's isoelectronic to this guy. Isoelectronic, what does that mean? Iso, same. Same electron type configuration type, okay? All right. What about this nitrogen here? What's its hybridization? And can you graph it? Well, there's a lone pair, right? Lone pair. Got to be. If there was no lone pair, there'd be a charge, and if there was a charge, it should have been shown. Nitrogen's neutral. It's got to have a lone pair to be neutral. Standard bonding. How many regions around the nitrogen? 4. Hybridization? sp3. And so we have, well, I mean, there it is right there, except only one bond's to hydrogen. The other 2 bonds are to carbon. So we got sp3. It's isoelectronic to the one we just did. See, this is carbon with a lone pair. Carbon with 3 bonds and a lone pair is a negative charge. Nitrogen with a lone pair and 3 bonds is neutral. But otherwise, it's isoelectronic. sp3, what type of bonds do you see the nitrogen making? Sigma bond to H, sigma bond to carbon, and the lone pair, correct? Lone pair in an sp3 orbital. Those electrons are spread out in a tetrahedral manner around the nitrogen. Now, I don't do any atomic geometry like y'all did in Gen Chem. You might say, well, isn't the bonds, what is it, trigonal, pyramidal? I don't talk about that because I don't ignore the lone pair. I always just call this tetrahedral. Bond angles are 1 and 9.5. There you go. You know, et cetera, et cetera. This here. How about this nitrogen here? First off, what functional group is this? Nitrile or a cyano group. Okay. What's the hybridization of that nitrogen? First off, there's a triple bond here, correct? And the nitrogen has a lone pair. So that's sort of really condensed down. You need to know structure there. How many electron regions around the nitrogen?
4.
Triple bond region, lone pair region, 2. So we expect what? sp. How many hybrids does an sp have? 2. What's left over? 2 p orbitals. And the question we want to answer is this lone pair is in what type of orbital? What type of orbital is that lone pair in? Hybrid or p? What type of bonds do you see the nitrogen making? Sigma bond to carbon. A triple bond is what? 1 sigma and 2 pi. And 2 pi. Pi is made with p's, right? Right? There's your triple bond. So the lone pair must exist in what? Yeah, the lone pair is here. And it's in a hybrid. That is, if you drew this nitrogen out, the hybrid set your geometry, okay? Fat, long, whatever, they're sp, you know the difference between sp and sp2. sp2 would be longer, but there you go. On one side's a lone pair. Over Over here, it's carbon, right? What's the hybridization of the carbon?
Which one?
The carbon that it's bonded to. Triple bond and single bond. SP. So it's also SP. It's got two p orbitals. This has two p orbitals. One each overlapping this way, and then one each overlapping that way to make two additional, or two pi bonds between here. I'm not going to finish this out. But that gets you a triple bond. The lone pair sits in the hybrid going in the other direction. Okay? Graphing, very useful in my opinion. Okay, how about this nitrogen of Lipitor? Hybridization. Okay, this nitrogen is going to be an exception. It's got 4 electron regions around it. We have a lone pair, 4th region. You might expect sp3. That's okay. But this was in the pre-course worksheet. We saw the first time this exception. This is actually sp2. We'll explain why, and we'll make a statement, but let's just start by saying that. Nitrogen's sp2. Since it's sp2, let's graph it. And answer the question, what type of orbital is the lone pair in? First off, if it's sp2, we have 3 hybrids, correct? Energy. What's left over? 1p orbital. sp2 is always like this. It doesn't matter if it's nitrogen, boron, oxygen, whatever. Okay, what type of bonds do you see the nitrogen making? Sigma bond to H, and then what? Sigma bond to carbon, sigma bond to carbon. Okay, where does the lone pair have to be? Yes, the lone pair is in p orbital. This nitrogen is neutral, correct? That means it has 5 valence electrons that it brought to the dance. 5 arrows, 1, 2, 3, 4, 5. Those are your 5 electrons. But it needed to make 3 bonds to get an octet. There we go. This is preferred. If it had been sp3, the lone pair would have been in a sp3. Okay. It's preferred, it's lower energy for the lone pair to be in a p orbital here. Why? Because of something called conjugation. All right. Now it's in a p orbital. Well, let's do this first. What's the hybridization of the carbons next door? How about the carbon on the right? sp2. How about the one on the left? They're both sp2, meaning they both have a p orbital. Okay? Both of those carbons have p orbitals. Now, yes, that p orbital is interacting with this p orbital to make that pi bond that's shown, and that is, okay, it continues that way. But the lone pair here, it's more stable to put it in a p orbital. The p orbital. So we get these p orbitals that can interact. If you can line up p orbitals, the more you can line up together and get them interacting, the better it is. This is called conjugation. It's the foundation of resonance. And this is why we get the exception here. It exists like this instead of sp3. That is, it's more of a trigonal planar geometry than a tetrahedral. That is, the bond angles, for example, between HN and carbon are not 109.5, but they're closer to 120. all this is the same thing. It's more like SP2. If it was SP3, two in the plane, one forward, one back. And so if those bonds are in the plane, the H bond back, the lone pair forward. Okay? Lone pair forward. See, if the lone pair is forward, it cannot interact with those p orbitals. So what happens is instead, the geometry changes and the lone pair moves more into the plane in a p orbital. And it exists like this. We'll talk about this more. That's an exception. Here's the take home when this exception takes place. Whenever a lone pair is next to a p orbital, and in this case it's next to one on each side, the lone pair is going to want to be in a p orbital itself. Hybridization of this nitrogen. There's a lone pair there. Hybridization. Hybridization. There's 4 regions around it, but it's actually also sp2. And the lone pair is in a p orbital. Why? Because there's p orbitals next door. You put it in the p orbital, then you get all these p orbitals lined up, like toy soldiers. But this nitrogen was what? Didn't we do that one? Was it Prozac? Did we do that one?
Yeah.
Was it down lower? That nitrogen was what? Yeah, this lone pair was in a sp3. Is there any reason for it to be in a p orbital? No, there's no p orbital next door. So it's not going to be in a p orbital. Hybrid is actually a lower energy orbital. And if there's nothing going on, it would rather be in a hybrid. This is actually in a higher energy orbital, but that actually leads to lower overall energy for the whole system because of the conjugation. Word of caution, this only happens when it looks like sp3, but it ends up being sp2. I say not only. It's rare that it happens when it looks like it should be sp2, but it ends up being sp. That's more of a rare exception. We'll address that when it comes up, if it ever does. Hybridization of this oxygen in graphic. Lone pairs. 2. Hybridization of that oxygen.
SP3.
Why? Yeah. Well, so did that nitrogen. Why did we make that one sp2? We didn't do it. The molecule did it. Why did the molecule want to be sp2?
Well, it doesn't have 2 different pi bonds.
What was the take home? Anytime a lone pair is what? Next to a p orbital, it's going to want to exist in a p orbital. There's a p orbital next door, right?
So you only do 1?
Yes.
Oh.
Good. We got 2. Yes. Only one lone pair, because if you made both of these in p orbitals, they both can't interact with this one. Okay? This is sp2. And if we graph that, I'll try to do it right here so we're not too far to the side. sp2 is what? Boom, boom, boom. 1 p orbital. What type of bonds do you see the oxygen making? Sigma to carbon, sigma to carbon. All right, we're in the lone pairs. One of them is in a p orbital. Why? So it can interact with the next door p orbital, and you get some p orbital interaction called resonance. But the other lone pair is not. The other lone pair is in a hybrid. So if you drew out that geometry, cut that off. What geometry is this? Trigonal planar. So it would be like this, right? But what is this? This is an orbital. What's in this orbital? Lone pair. Sometimes you can see a lone pair drawn like that to indicate direction. Okay? I mean, that's really an orbital. That's an orbital. But there's your trigonal planar. One lone pair contributes to that trigonal planar. And then the other is a p orbital. Now it's coming straight out at you. You know, we could sort of just draw it there. And you got one here. And there's a lone pair there, and it's interacting. But that would be coming out at you if you drew the planar there. So one lone pair is part of the planar system, and then one lone pair is in the p orbital doing the resonance thing. Question?
Was there ever a case where both lone pairs would be in p orbitals?
And it would be SP. That's the thing I was trying to explain before I started this. We'll cover it when if it ever comes up. That's only going to happen if there's two p orbitals on the same atom next door. And that's going to be quite rare. If you check the tape, I first said it will never, or something like that. Then I said, well, it can, but it's just highly unlikely to see it. And usually it's only when it looks like sp3, but it ends up being sp2. Hybridization of this fluorine. sp2, but one of the lone pairs is in a p orbital, correct? One lone pair in a p orbital interacting with the next door p orbital. The other two lone pairs in hybrids. Graph it, you'll see it. sp2, the fluorine's making one sigma bond, right? Graphing. You can do any of these. And then you could ask, show me real quick. By the way, the structure of Cipro is correct there. It's incorrect on one of the sides of the DQ page. It's missing the cyclopropyl ring on one side. It's correct there. Questions here?
Is there a reason why the lone pair, does it always project outside of the chemical? Or is that just the way it's drawn? So like in the sp2 on the Adorbass statin that we discussed, the H is kind of going towards the inside of the chemical, and the lone pair and the p orbital is projecting out. Is that normal? Doesn't matter.
Which compound? I don't think it's really relevant. Which compound you talking about?
The Adorbass statin, Lipitor.
Lipitor. Atorvastatin. The statin. Lipitor. Which one?
That one right there.
This lone pair?
Yep.
What do you mean? It's not projected really.
So is it more energy favorable to be project outside of the p orbitals, project outside of the chemical versus towards the inside?
Well, terminology. We call it a compound.
A compound.
Compound, not a chemical. That's just a better term. I don't understand what you mean projecting out. It's in a p orbital. The p orbital is perpendicular to the plane. You can draw the plane any way you want it. Just like when I do it on the paper, I can hold it any way I want it. If I'm holding it like this, the p orbital is like this. If I'm holding it like that, it's like that. It's just,
Maybe I'm just misunderstanding.
ask me again, but I don't, however you want to draw it. I mean, it's trigonal planar and the p orbital is perpendicular to the plane. Okay, we need to move along. There's plenty of questions, such as in the workbook. There's a drug page there, hybridization, DUS, formulas, et cetera, et cetera. Lab this week, solubility. Any questions about lab? Questions about lab? Alrighty. Physical properties. Intro, warm-up questions. Other warm-up questions. Polarity of covalent bonds. H2, nonpolar. Okay. We got 2 electrons here, right? That's the covalent bond. Something like H2, they're equally shared. The electrons sit very symmetrically between the 2 hydrogen nuclei. Considered a nonpolar bond. HCl, on the other hand, is a polar bond. 2 electrons here, but chlorine, because it's way more electronegative, it's electron greedy, it pulls the electron. So even though they're bonding, the chlorine is really doing this. All right, it's like, hey, we can indicate this with a dipole arrow. In terms of distribution here, it's something more like, the 2 electrons are just kind of closer to the chlorine. This is the idea of a polar covalent bond. Now, if the chlorine just totally took these 2 electrons and separated, we'd call that ionization. That's the extreme. And the chlorine would then have an extra electron, it would be negative, and then the H would have nothing, and it would be positive. But in the covalent, there we go. We can illustrate this with this arrow here, electrons being moved this way, and a positive over here, because if it's missing electrons, electron density, it's not a formal charge, it's sort of a partial charge. We can also show the partial charges like this. So the chlorine is partial negative due to the polarity. Your carbonyl compounds, polar because the carbonyl is polar. Oxygen more electronegative than carbon. The electrons being pulled towards the oxygen. Shown like that or this. And so the carbon of your carbonyl is electron poor. We'll also call it electrophilic. It would love to have electrons. And so carbonyl compounds tend to be polar as a result of this. Okay, we need to be able to assess polarity. First off, of individual bonds, such as diatomic molecules. This would be an interhalogen, ICl. Polar because Cl is more electronegative than iodine. Electrons being pulled. It's the same situation as this, except you got an iodine instead of a hydrogen, right? What about BrCl? Which halogen is more electrophilic? Which atom is more electrophilic? What does electrophilic mean? What?
It wants more electrons.
You gotta be careful. That sounds like electronegative. Chlorine's more electronegative. Because of that, the bromine in this situation is more electrophilic. An electrophile is an electron poor species. Okay. It can be sort of conflicting terminology. Electrophile. Something that's electron poor is going to love to have some electrons. It will love electrons. So it almost sounds like electronegative. Chlorine more electronegative, thus we get dipole this way, right? Bromine partial plus, chlorine partial minus. The bromine is more electrophilic. That means in this situation, which one's going to want electrons more? Actually, the bromine. Because the chlorine's already got them. It stole them because it was electronegative. Leaving the bromine electrophilic. We'll use that terminology as we go along, and it'll become just commonplace. Starting it now, though. Polar molecules, right? Okay, how about water? Is it polar? Now we've got 3 atoms here, right? 2 individual dipoles. So oxygen pooling, leaving this partial plus. Oxygen pooling, leaving this partial plus. Partial negative here from the pooling. When you got multiple dipoles, you need to ask, do they cancel out? Because if they cancel out, then it will be just nothing. It'll be nonpolar. Do these cancel out? Because it's what? Yeah, it's actually been tetrahedral. Now, these are not equal and opposite. They are equal, but they're not exactly opposite because the true nature of water is lone pair, right? Tetrahedral, okay? And this is 109.5 approximately. That can vary. And so, are these dipoles opposite to each other, canceling each other out? Like vector addition, y'all do that, some of that in math or physics? No, these do not cancel. They actually sum up to make a single dipole straight like this. That makes sense. Partial positive area, partial negative. That makes sense because this is electrons. That sort of reinforces the idea. So we have a net molecular dipole moment with this direction, coming from summing up the two individual dipoles. Yes, water is a polar molecule. Because that's not the correct geometry. So you got to know correct geometries to judge if your dipoles are canceling. This is just another idea of electrophilic. Carbon-bromine, the carbon's more partial positive, bromine partial negative. We have a dipole here, making the carbon partial positive and electrophilic. Knowing that this carbon is partial positive is going to influence reactivity later on. Okay, let's do some more examples. We've already done water, yeah, polar molecule, a net dipole moment. With such a direction drawn on the molecule, chemical. What about CO2? Polar or not? Structure? Well, hopefully you'll be able to put together a structure of CO2. There's a page of Lewis structures in the workbook. How are we doing with those? Questions? CO2 here. Is this a good structure? Is the geometry correct of the three atoms? Is it linear or is it something else? What's the hybridization in the middle of carbon? SP, correct? SP, linear, there you go. What do we have? Boom and boom. Oxygen pooling, leaving the carbon electrophilic, electron poor. Are those equal and opposite? Yes, these vectors are equal and opposite. CO2 is what?
Non-polar.
Nonpolar. CO2 is nonpolar molecule. What does it mean to be nonpolar? What does that matter? What's the consequences? Is our discussion finished right there, or what does it mean to be nonpolar or polar? What about solubility? A more polar compound is going to be soluble in a more polar solvent, because light dissolves light. A nonpolar compound is going to be more soluble than a nonpolar. What about its orientation in an electric field? Or response to some type of electric field in physics? Is that going to respond to an electric field or something? I don't know. I haven't been in physics in a long time. If you got a polar molecule, what does it mean to be polar? You got a positive end and a negative end. That's what it means to be polar. And such a compound is going to experience a torque if you put it into an electric field. Okay? So there's many consequences that you can then go on and talk about after you identify this answer. Please think about it. I need to do the rest of these. So obviously you need to have a Lewis structure, and then you need to have correct geometry, then you need to be able to assess your individual dipoles and sum them up. SO2, polar, not polar?
Polar.
Why? Very good, lone pair. How do you know he's got a lone pair? Et cetera, right? I mean, we started day one with doing that type of stuff. And then these others, these should be pretty darn simple. They're just common carbon compounds. Please do those. We'll look at them first thing next time. Ionics. As I mentioned, ionics is the extreme. Sodium chloride. We're not quite done yet. Sodium chloride. Is that a covalent bond?
No.
No, it never was. That chlorine takes these two electrons. It just takes them. Two electrons move and it exists ionized. It never was covalent. So I'm talking about the extreme there. For next time, we'll be looking at physical properties such as boiling point, melting point, solubility. Please look ahead. We'll start by seeing if you have any questions about these topics. Maybe some of you in lab tomorrow. I think we're meeting downstairs, the room over there. Room over there. Yeah. Have a good day, guys.